Let's talk. Before we hit up dilations, I need to go over one term with you. Invariant point. Wait till you hear this one. Invariant point. What's an invariant point? Points, ready? That do not move after a transformation. So wherever it started, that's where it finishes. All right, so points that do not move after a transformation. So A and A prime, same exact point. Same exact point. So what do you say? Let's see this in action now. I'm giving you quadrilateral A, B, C, D. No need to graph. There's no need to graph this. You see points A, B, C, and D. All right, question, first one. I'm going to ask two people here to give me a transformation, reflection, rotation, translation, that will result in point B being invariant, meaning you give me the transformation, I perform it, B is still at 0, -3. Didn't move at all. All right, so let me give you a little visual here. Here's point B, 0, -3. I need somebody to give me a transformation and be specific so that that point will not move anywhere. It's going to stay right where it is on that graph. And I know I'm dealing with honors level students, so can we get the funny business out of the way? Let's do a translation of 0, 0. Let's get out of here. All right. Oh, how about a rotation of 360? No, I don't want any of that. All right, funny? Not at all. Just funny looking. All right. So give me something else then. I don't want translation of 0, 0. I don't want a rotation of 360. Give me something I can do to point B where it would stay exactly where you see it right now. I think we got something here. Will?
A reflection over the y-axis.
Oh, there you go. How's that look, kids? If I reflect B over the y-axis, it's not going anywhere. Good. But we are in honors, so one's not going to cut it. I need something else. Come on. Dig deep. What else could I do other than a reflection over the y-axis now? There's somewhere else I could go here, and it's not moving. It's not moving. Max?
Any rotation around, well, centered at 0, -3.
Okay, that's like my 360 one. Yeah. Okay. I'm looking for a more specific, something more specific.
Oh,
all right.
A reflection where y.
We're almost there. Over what line?
Y goes -3.
There we go. Horizontal line going through -3. I could reflect, and that point's not going anywhere. Good job. All right, now that you get the hang of it, how about point D? Give me a transformation where D will be invariant. Again, D, here you go. You need a little visual right up here. 1, 2, 3. Here's point D. I wanted a new color. Point D. There it is. Give me something there. All right, now I can go numbers. I feel comfortable going numbers. 22. Give me something.
Reflection where x equals 3.
Wow, you went to the tough one right away. Respect. Went to the tough one right away. Reflection through the line x equals 3 because that's a vertical line. Or I could do what else to make it invariant, not move. 8. Reflection over the x-axis. Yes. There you go. All right, so I just wanted to establish that vocabulary term, invariant. The points do not move. Invariant, points do not move. All right, are you ready here? You thought you knew what a dilation was? Not a chance. Let me ask you, what's your background with dilations? Something gets bigger or something gets smaller? Okay, that's what figures do, get bigger or smaller in dilation. But what about a point? What happens when a point gets dilated? Are you telling me this happens? Get out of town. All right, that doesn't happen. Points don't physically get bigger or smaller. The objects do. So let me show you what actually happens in a dilation. You need two things for a dilation. Two most important things to a dilation. Number one, you need a center to dilate around. Okay, you need a center to dilate around. When you perform a dilation, here's what happens to a point. It either gets further away from that center or it gets closer to that center. How do I know if it's going to get further away or closer? Here's the second thing you need in a dilation. What's called a scale factor. Notice it, look at my first diagram, it's on your paper. I have a scale factor of 2. What does that mean? Well, first, everyone sees my center of dilation. Look at point A for me. Point A is a certain distance away from that center. All right, I don't know how far away, but it's a certain distance. A scale factor of 2 tells me double that distance away now. Now the point is getting closer or further away? Further away. So right now it's got a certain distance to A, and I'm about to double that distance. So it gets further away. Look at my second diagram here. Now I change the scale factor to a half, 0.5. What are the points doing now? Take a look. Are they getting further away? No, they're getting closer. How much closer? Half the distance closer. All right, so that's what you need. You need the what point am I dilating around, the center of dilation, and the scale factor. So looking at these two diagrams, can you make a little summary for me? If the scale factor is blank, the figure is going to be an enlargement. If I tell you the scale factor is, what do you think? Guesses.
Greater than 1.
Kyle?
Greater than 1.
Greater than 1, correct. So if the scale factor is greater than 1, the points are going to get further away from your center, meaning the object's going to get larger. See what happens with the dilation now in their points. All right. What about the scale factor results in a reduction? Smaller figure. The points get closer to the center. And don't just say less than 1 because we're not going to deal with negative scale factors. So I need that. Don't say less than 1 because I need something more detailed. Less than 1 means it could be negative, and we're not going to deal with negatives. And that doesn't mean a reduction either, just because it's negative. Kyle, you're going to go down this one?
Greater than 0, less than 1.
There we go. A scale factor between 0 and 1. Good work. That's what happens. The center of dilation is the most important part. Am I getting closer to it or am I getting further away? Let's actually dilate a point now. This will be important at the end. What is point J right now? What is point J? What, 3, 2? All right, I'm just going to jot that down. That point J is 3, 2. That's going to come into play at the end here when we fill in the blanks down here. All right, so how do I actually dilate? Take point, part A. Take point J, dilate it around the, what's my center now? What's my center? Well, the origin. The center's the origin. Dilate it by a scale factor of 2. Before we actually do that, predictions. Is J prime going to be further away from the origin than J or closer? Further away because the scale factor is bigger than 1. So how do I figure out where J prime is? Ready? I keep mentioning the word distance. Good news, we're not going to use the distance, but we don't need it here. We're going to use slope. Watch, we're going to use slope. So from the center, 0, 0, where we dilate around, how many up and over do I need to go to get to J? Up and over from 0, 0 to J, what is it? 25? Up 2 over 3. Scale factor of 2, double that. So instead of going up 2 over 3, we'll go up 4 over, that's how you dilate. Instead of going up 2 over 3, now we'll go up 4 over 6. And there's J prime. Which would be what? I want to write it down too. 6, 4. The scale factor will tell you what you do to the original distance. All right, now let's go in reverse. Scale factor of 1/2. Is J going to get closer? J prime going to get closer or further away from the origin? 1/2. Scale factor of 1/2. Further away or closer? Closer to the origin. All right, well, we just figured out we went up 2 over 3. Cut it that distance in half now. Now I want to go what? Up 1 over 1.5. Up 1 over 1.5. Here's J prime now. Scale factor of 1/2. J prime, what are we looking at here? 1.5, 1. Good. One more. Let's do a scale factor of 3. Now it's really going to get further away. Up 2 over 3. Now you're going to go what? Up 6 over. Let's do it. Up 6 over 9. There's J prime. 9, 6. All right, something special happens when your center of dilation is the origin, where maybe I don't have to go up and over, triple it, up and over, cut it in half. There's a different way I could get to my point if it's around the origin. Here's what I'd like you to do. Remember we wrote point J at the beginning was 3, 2? Look at all the ending coordinates and the scale factor we used. You tell me how I can get to J prime quicker than counting on a graph. We started at 3, 2. J was always 3, 2. Look at my ending points and the scale factor I used. What can I do to find J prime a little quicker than just relying on up and over on the graph? So I went from 3, 2 to 6, 4, and the scale factor was 2. 3, 2 to 1.5, 1, and the scale factor is 1/2. What can I do quicker than what I just set up here? Alicia, what do you have?
Times it by the scale factor.
Multiply your coordinate by the scale factor. There you go. So only, darn it, only, listen to it, only if it's around the origin. This only works if you're dilating. If I dilate around another point, which we will do in a second, this doesn't work. It's got to be around the origin. Multiply the coordinates by the scale factor. All right? But only if you're dilating around the origin. The center is the origin. Oh, but what class are we in? Yeah, honors. Are we always going to dilate around the origin? Absolutely not. So what do I do then? Same thing we did before you knew the rule. So now I'm going to dilate around 7, 1. So everyone find 7, 1 on your graph. Now I'm going to dilate around this point. Okay, so I just can't multiply by 2 now. That's not going to work because my dilation's not, the center's not the origin. All right, so how do I perform a dilation of 2? Same thing we just did, ready? Going from 7, 1, how many up and over do I need to get to J? 24, up and over how many? Let me guess, not here. 19. 11?
I'm here.
Oh, we're so lucky. Up.
Up 1 over 4.
Okay, so I'm doubling that. So now go up 2 over from the center, not from J, from the center. Everything is done from the center. So up 2 over 1, 2, 3, 4, 5, 6, 7, 8. J prime, negative 1, 3. My last piece of advice here, because I'm going to let you go in your group now, you should never have an image that's on the other side. Okay, you should never have an image that's on the other side of your center. Okay, never should have it on the other side. It should always be on the same side as the center. All right, so go ahead in your group, go ahead through B and C, and I'll ask you what you have. Because there's not much else I need to show you here. So now cut that distance in half. Center to your point. Always go from the center to your point that you're dilating.
5, 1, 1/2. Negative 5, 1.
Hey, can I get a part B? Where's J prime go after a dilation of 1, half, 12, 5, 1.5? And how about part C? Now I dilate by 3, getting even further away than part A. 26,
Sorry, negative 5.4.
negative 5.4. Thank you. You can dilate a point, you can dilate a figure. All a figure is a couple points now. And I'm pretty much done teaching here. I want first make sure you can work in your groups here. On number 3, you can take a look up here to see what the ending result should look like and the coordinates. And then I'll walk around, see where you guys are, and then you can move on to number 4, and I'll put the answer up here as well. There's no need for me to keep calling on numbers and here you go, champs. Here you go, next one. Okay, make sure we all match there. And also, as most of you can see, I'm making a note so it doesn't get skipped over on homework. Number 30 asks you for the perimeter of a figure, and you're going to need the distance formula, so here it is. All right, so we don't get any excuses on distance formula. And you have half the class, so most of you will probably get to number 30 before you leave. But just make sure this is solid. If not, call me over here because we're not. This last problem, you are not dilating around the center of the origin.
No problem. Two sections. What?
You ready? You want to do it now? Okay. I'll give it to you.
Graph.